Hey guys, this is my first programming video, so if I make any mistake, I apologize in advance. So today I'm going to discuss about this problem. It appeared in a contest on LeetCode last week. Um, I found it very interesting and trickier, although at the time of contest I was not able to finish it up. I was getting TLE, but I didn't find the better solution or optimized solution. It's pretty interesting, but at first glance, if you look, that count the pairs with XOR in a range. So meaning that you have to find all the pairs of these numbers 1, 4, 2, 7, and etc., whatever your number array is, and you have to XOR the two elements, and you have to check that the XOR value is greater than 2, which is low, and smaller than or equal to high, meaning less than or equal to 6. So if we look into this example here, look at 1 and 4. If we do XOR, it will be 5. 5 is of course greater than 2 and the smaller than 6, so we will count this, and we have to find all those pairs. So it looks pretty straightforward, meaning that you have to find all the pairs. Finding all the pairs is also not problematic. You will probably do integer I equal to 0, I less than should be the nums dot length, ngth, length minus 1, and then I plus plus. So why length minus 1? Because we need two pointer for like kind of a pointer assessing solution. There's a 1, 4, 2, 7. So when you go to the last element, your one of the pointer, one of the pointer should be here, and your rightmost pointer would be here. So the limit of the first pointer has to be ended here. So that's why length minus 1, and then the next one, integer j, will be starting. Think about like when the first element is this 0, so the second, the rightmost pointer has to be here. So meaning that j equal to I plus 1 would be restarting, and it can go end of the array. So j less than nums dot length, and then j plus plus. So in that case, if you do that, you will find all the pairs. The pairs will be what? Let's say the first number would be nums of I, and then integer y would be nums of j. So we can even check that all those pairs. System, let's print it out. System dot out dot print println. We can say x plus, and then dash plus y. So that's it. Now let's remove this line. See if we can find all those pairs. Pretty straightforward. Now here probably we will return 0. Let's run the code. See what happened, what it prints. Look at that. So 1 4 1 2 1 7, and then 4 2 4 7, and then 2 7. So that's all the pairs. So when you have all the pairs, you can do XOR. So finding an XOR is pretty easy. Equals to x here. This is the XOR sign in Java. You XOR it. Now you have to just check that if the result is greater than equals to low and result is smaller than or equal to high, in that case you will just increase the count plus plus, or you will say count plus equals to 1. That also works. So what is that count? The total count. We will say integer count equals to 0. That's it. Now we will return the count. Let's see what it does. If we run the code, so it looks like it's giving the expected result. Let's don't print it because printing will take extra time. And if I submit, look at that, what happened. And as you already see, so let's keep running. See the time limit exit. So this doesn't work. So what can we do to solve this problem? Let's go to the real discussion. I'm going to clear this problem. So to solve this problem, since our approach is fine, somehow we have to find all the pairs quicker in a manner that it take lesser time. Basically, if you see any number, it's binary representation, we can take it, that binary representation, as a starting point to find all the numbers. Let's say if you have a number which is 1, 0, 0, which is 4, and then let's say the number is 3, in that case will be 0, 1, and 1. So look at that. If we want to find number in a range or grouping together, we can leverage that value. If you see that the first bit is 0, and let's say our target, if the target is 4, or let's say high is equals to 4, and we want any XOR value below 4, we can check the bit. That if that bit is like 1 or lesser, probably this number would be in our range. Now, how can we find all those pairs? So one way to find would be to create such a data structure that it will give or find those data quicker. That data structure is called try. So how the try works, try is basically good for prefix search. So what does it mean? It means this. Let's say we have a word like dog, D-O-G, dog, and then we have word like dawn, and we have word like DP, which is dynamic programming, and we have word like, let's say, DUP, dope, or DO. So we want to find that how many words start with D or prefix D, or how many words with DO. So if we have this kind of situation, we can use a easy data structure called try. So how to build this? Let's start with the dog. So D, and then it comes as an O, and then G. Next one, dawn, D-O. So we can say N here. And at the same time, even we can count. See that the first word is going through. We can say here 1, and then we'll say 1. Each time we iterate over the node, whatever the existing value is, we will add 1 with it. So again 1, right? So now when it is dawn, starting over, we'll say 2, and this will be again 2, and dawn, this one is 1 because previous value was null or 0. And then the DP, so D, it doesn't go with this one, so P. So when you do that, you have to increase this one. So what is the value will be here? Because it's a new word, we will say 3, because it was 2 before. So now it is 3, and here is 1. And then let's say DO, so D, it will be 4. So this value becomes 4, and this value come down to, not come down to, it goes to 3, because 2 plus 1. So if I say now that how many words start with D, because easily 4, right? 1, 2, 3, 4. And how many words has it started with DO? That's pretty straightforward. Go D and O. How many words has it started with? Looks like 3, right? So DOG, DON, and then DO. So 3 words. So we will leverage this similar principle, but we have to find with the all those bit operation, that each of this number represented by bit, we will take that approach. And another thing is that from the binary representation, look at that. Let's say if you have a number, okay, so let's say 1, and say 0, 0, right? So what is the maximum number it can represent? Maximum could be 1, 1, 1, which is 7, right? 1, and then 2, and then 4. So 7 it can maximum generate. So if any number, if we want to XOR with it and find into the limit, we can take this node, and that how many number has or started with this node. So we can easily find out that the XOR value, it match in the range or not. Okay, so let's start. To do that, I'm going to hide it now. We need, first of all, we need a node, which will be our prefix node. We'll say class node. It will have integer count, or you can say cnt, and then there will be another one. We'll say node array. We'll give the name child. Now let's create a constructor. Say node this. It doesn't take any parameter. This dot cnt. The first value always start with 0, and then the child. Each of this node, if you see, since it's a binary number 0 and 1, so it will have always 2 node, say 2. So this will hold our node data structure, which is pretty good. And then the next, we need to start operating. What we are going to do is, each time we will check that whenever we take a new number, we will see that how many numbers are there already in the try that will give a XOR operation into that boundary. We will update, or we will count that number. So let's start. We need to have a root, new node. So this is our root, and then we have to check each of these number, take the number and see how many number it create the XOR with. But before that, we are looking to count the pairs. So we'll say the count pairs is equals to 0, and then for each number, integer, okay, num and nums. So it gives all of our number, and then we will have to check that how many numbers it create with the XOR with the target, and then we will add it, the number, to the tree. So we will say that insert this number, and then definitely root, oops, okay, root number, and then we have a target. So do we need that? We don't need it, just this. But before that, here we have to compute that boundary. Now what we are going to do, that we will see our maximum limit, that any pairs match, it has to be below high. It has to be below high. So we will start with like high plus 1. So it will be always below high. And for the law, we will also do the same thing. So in that case, what will happen is that if we find all the number up to high, and then all the number up to low, and if we subtract, that middle is our range, right? So let's say 1 2 3 4 1 2 3 4 5, right? So first iteration, if we up to high, like up to 5, we will get all those number, and the second operation, say law is 2. In that case, if we cover up to this 2 and then subtract, this will left over 3 4 5. So that's pretty straightforward. Let's do that here. We will say count pairs. This is our variable, plus equals to, then whatever the count we came up with. So we will say count smaller. Count smaller. What will be our maximum range? High plus 1. This is our maximum range. What we need our root, and then the current number. Okay, so that will give you this, and since this will be the bigger, so we are putting it fast for the subtraction time. It will cover a lot more number. So similar thing, we'll say count smaller. So we'll get root, and then number, and the low. So it will cover it. Now let's implement this function, which is called count smaller, and we have to implement this insert. So insert is would be pretty straightforward. Let's start with that. Private void insert method. What it takes a node, which is root, and then it takes a number. Now since this problem, if you see the constraint, 2 to the power 4, so we can create our constraint up to like 14. Okay, so that will be a lot more easier. Okay, so here what are we going to do is we have to find each of these bit, the binary bit. We will consider up to 14. I equals to 14, and then I will keep coming down up to 0, and then I minus minus. So now how to find the most significant bit, because this is where we will start, right? To find that, we'll say num, we have to move a right shift I, and then we have to what we have to do with ampersand with 1. If that result is 1, that is a bit, so we know that this is the most significant bit, whatever it is. It could be 0 or it could be 1. So now what are we gonna do? That we have to insert into our root of the tree. So let's start with that. So root dot but for the first time our root or the child might be null, so we have to check it. If root dot child, and then we will give this bit is equal null, what are we going to do? We have to add a new child under that. So root dot child, and then we'll say bit equals to new node. So we'll have a node now, which is fine. Then we need a counter, right? So root dot child of bit, in the case our variable cnt count plus equals to 1, so it will be added a new node, and we have to update the node, right? So root dot child, we will pursue that whatever the bit is. So this will be our new root. Let's update that. Pretty straightforward, right? So this is how we can insert to our tree, but this method is still we have to implement. So let's implement that method. So we'll say private integer, method name is count smaller. We have node, which is root, and then integer n and integer k. So here k is our limit. So integer count, again pairs, because for each of this number we want to return how many numbers it will make the XOR with in between the limit, right? So it will send a 0, and we will do the same thing because we have the 14 digit or like 14 bit, 14 number of bit. So let's start with that. Integer I equal to 0, I greater than equal to 0, I minus minus. Okay, is it right? Yeah, looks like fine. So we have to now our target, which is k, that will give us a hint that this number, if I do XOR with, will it be in the boundary or not? So each of this root in the tree, if you see that this is the maximum value, right? If our current number is equal or below this, that means it's a good number. We have to check that how many other number already in the tree it becomes the XOR with. And XOR, we have to always, XOR value becomes 1 when they are opposite. So it's a good clue to remember. And here another should be that condition to check the null, that root not equals to null. Okay, so from here now let's first find the first bit of our number itself. It is x, which will be here, n, and then the right shift I, and then end 1. So that will give out the most significant bit, integer y. Here we will be using the k, make the right shift I, and then ampersand 1. So now we both have the most significant bit. What will happen that if our target root node is 1, that means that target number is the biggest. It doesn't matter that this X number is still 1 or 0, because if it is 1, that means it will be equal. And if it is 0, it's smaller. So it's still fine, but we have to check that how many number it will have an XOR with in this boundary. So do that. We have to check that root dot child x not equal to null. If it is not equal to null, that means when y equal to 1, all the other number in the existing tree, we have to count it. So count pairs plus equals to root dot child of x dot count. Same thing, right? So there you go. And then since we are looking for the XOR operation, we will follow the path which is other than the current number's bit. So let's say whatever the, if x is 1, we have to go to 0. If it is 0, we have to go to the different path, because whenever it is reverse, that's when it makes all the number, and already we are counting for the existing node. So let's go to the other node. So how can we go there? Root equals to root dot child of 1 minus x, so it will reverse it. But what happens if it is not, meaning that it's on the different branch? So the target value bit was 1, but our number is 0. So in that case, just follow that path. Root dot child and follow that x. Follow the path, and then when all of this operation is finished, return count pairs. That's about it. So let's run it and see what happened. If we run, okay, line number 9. Okay, we forgot that. Sweet. Okay, line number 11, there is a missing return statement. Oh wow. So let's return count pairs. Start it again. Okay, so that doesn't work. Something went wrong. We have to see what went wrong. Let's figure it out. Okay, then I, which is fine. Okay, count smaller, I, and then the law, which is fine. Okay, did insert root and the number pairs, which is good, and then go to the count smaller. In that case, count smaller is to 0, equal to up. So this is where is the mistake. We have to start with the 14th. Okay. So it looks like it perfect. Let's run it. Awesome. So it got accepted. Looks great.